section 10 in the higher book is all about real life graphs, and this corresponds to chapter 13 in the foundation course, hence the common background. Now in chapter 13 there are plenty of distance time graphs, and these are shown in section 10.1 on page 108, 109. I won't do any of those because the same questions have been covered. So you look at the foundation videos and click on the link that says link to essential foundation videos and look at those first. What I will do is start with some questions in section 12.10.2. The reason being because it's called other real life graphs, different scenarios, different storylines, very interesting. So starting with that one, we've got question 1 there. It says the graph shows the temperature of a cup of tea as it cools. Essentially what we have is a cooling curve following the trend shown there in the graph on the right. What temperature is the tea when it was made? Well, I think we go between 80 and 100. We're looking at 90 degrees, aren't we? So 90 degrees C. How long does it take the tea to cool to half its original temperature? Well, half of 90 is 45, so that's going to be, let's have a look, that's 50. 45 is going to be about there. Let's use this little thing here to try and draw across. So that's half its temperature. Again, it's a bit difficult using this, so show the little arrow, we go across, then we read down. Oh, incidentally, that's a well constructed question. That is about 10 minutes, so make it fit there. Alright, next bit. Joe looked at the graph and said if it carries on cooling like this, it will freeze in another half an hour. Do you think Joe is correct? Explain your answer. Well, let me write it down there. Well, no, he's not correct. It will return to room temperature. Now, if the temperature of the room is 0 degrees C, then in fact it will freeze in half an hour or so. But where's this being conducted? We don't know. I presume we're not drinking our tea outside, are we? Doing the experiment outside in the winter. So no, it will return to room temperature. D. What about Max? Max says if the curve carries on curving like that, it will soon start warming up again. Do you think Max is correct? No. It will return to room temperature, but if the room temperature increases, so will the temperature of the tea. Alright, so there we go, that's Max covered. Next question. Right, this is question 2 on page 113, grade C rated. Now the following graph shows how power in kilowatts and torque in Newton meters vary with the speed of the engine in revolutions per minute for a given car engine. Okay, so we've got power, torque, the ability of the engine to turn and to cause acceleration to occur, and speed. Of course, you know about RPM, don't you? Right, so let's see what John's saying. John said that the torque was at its highest at 4,000 RPM. What was John's mistake? The torque was highest at 4,000 RPM. Well, actually, I can see the torque was highest at 2,000 RPM. So let me just state that obviously. So the torque was highest at 2,000 revolutions per minute. So what did John do wrong? He read the maximum value on the, there he goes, that's where he got 4,000 from. He read the power scale. He read the maximum value on the power graph. Is that okay? Right. B says describe any pattern in the graph showing torque. What have I got? Let's have a pattern. Okay, so let's say torque increases from 1,000 to 2,000 RPM. Is that alright? So we've got a general increase in torque. It decreases from 3,000 torque. No point to 3,000 torque. From 3,000 RPM, isn't it? Onwards. Okay, they're my patterns. Goes up to a certain amount, stays flat, then begins to come down after about 3,000 RPM. Alright, part C. Is it appropriate to continue the graph to predict values for 7,000 RPM? No. Why? Because there is no clear data after 4,500 RPM. What could happen? The graph could slope downwards sharply. This is my guess, alright? So I reckon it gets so inefficient at high revs, I reckon the graph could do something like this. It could suddenly go like that. So in other words, even if you're working about say 6 or 6,500 RPM, we're going to get very, very little torque out of the engine. So I'm just guessing. It's a suggestion. This isn't a science or physics question. It's trying to see what's happening trend-wise. It could in fact continue like that. Obviously it won't go down to zero torque, because obviously the turning effect generated by the engine is still going to happen, otherwise the car's not going to accelerate anywhere. But we can't assume that it will be a near linear decline in the amount of torque relative to the revolutions per minute of the engine, so we can't assume that. It could suddenly turn down like I've shown just there. Alright, and that's that one. Question 3. 3 is very interesting. Diagrams below show 8 empty bottles. Each bottle is to be filled with water at a constant rate. It's very important. The tap won't suddenly go fast and then slow to mess up the graph. 8 containers and 8 graphs describing what's going to happen to the depth of water as time goes on. Now, matching these is no guesswork. We've got to try and match the correct container with the correct graph. Now, the easy ones are question 1, 2 and 8. As you can see, they're cylinders. Obviously we have a two-dimensional view of the side of the cylinder, but anyway, they're cylinders. They have the same cross section all the way through. Whichever way you cut these cylinders and you look down, you're going to get a lovely circle there, and it's going to be the same diameter all the way down. Therefore, as water fills into these containers, that one, and that one, we're going to get a lovely straight line graph. Now, the narrower the cylinder, the quicker it will fill up. So I'm going to say B goes with number 1. I'm going to say C goes with number 2 because it's wider, therefore fills up more slowly. Look at the gradient there. And D is going to fill up really slowly because it's very, very wide. And I'll put D there. Right, let's look at this conical flask here, as in science. If we fill this up with water, and there's the water going in, it's wide at the bottom and narrower at the top, so we're looking for something to fill up slowly and then gradually increase and then go straight, because here we have the cylindrical part, so we're looking for something that's going to go slow, faster, 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 and then carry on going straight. Now what do we got here? I reckon I'm going to go with F, so there it is, slow at first and then accelerates as it gets straighter, accelerates as it gets narrower rather, and then we have a straight part of that. So I think F is taken with 3. What else? Let's go for number 7. It looks really interesting. Right, so I think the cut-off point for vase number 7 is fill up slowly at first, then go quicker, and then fill up more slowly. So I'm going slow, quicker, then slower, 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 because it's getting wider, wider, wider. Right, revise that. Slow, quick, slow. Sounds like a dance, doesn't it? So I'm looking for something that goes, starts off slowly, then fills up more quickly, and then starts to fill up more slowly again because it's getting wider. I'm going to put H with 7 therefore. What are we left with? Now these graphs, E and G, are very, very close indeed. It's going to be very hard to sort out what's going on with that one. I think I'll do this one. I think I've spotted that there. Now look at this lovely round bottom flask here. If I cut it down the middle there, you can see initially it's going to fill up very quickly because it's very narrow at the bottom, and then get slower to its slowest point when it's in the middle, because that's its widest point. Then after it begins to fill up beyond the middle point, it will fill up more quickly for the simple reason it's getting narrower and narrower. So I'm looking for faster, slower and slower, then faster and faster. So do I have a graph that goes slow, slow, and then fast, fast, fast? Let's have a look. Fills up quickly, then slows down, and then fills up more quickly. So there you go. I'm going to put 5 with A. That works. Now I've got 2 more graphs, 2 more vases. Question 6. I've got a cylindrical part, a uniform cross section across there, and then the vase gets wider and wider. So I'm looking for a straight line, linear part first, and then something that fills up more slowly afterwards, because the vase is getting wider and wider. So I'm looking for linear and then wider and wider. In other words, filling up more and more slowly. So I'm going to go with, I suppose, that one, because that looks straight-ish, and then it slows up as the vase gets wider and wider. So I'm putting 6 with E, and I'm left with G goes with 4. Now let me just see if I trust that. I think it's very badly drawn. What's happening is it's filling up quickly at first and then slowing up. In other words, the vase must be getting wider. There it is, filling up quickly at first, gets narrow, and then filling up more slowly as it gets wider towards that bit. Well, really, they've not represented the top part. The top part should be totally straight. They should have extended that a little bit for us, like that, just to show that, just to represent the filling of the widest part being linear. But anyway, I presume there's a little bit of a straight line there, but that's what I'm going to go with, and that's the kind of thinking you may need to put in writing if they get you to match cylinders with their graph as water fills them up, different shapes. You have to explain it, justify it in the way that I have done. So you need to watch this a few times, and now I'm going to stop because I've done enough for one video.